Hello, welcome to Chapter 4, Types of Chemical Reactions and Solution Stoichiometry. So you guys can see from the screen the types of things that we're going to be covering in this chapter. How do you make solutions? What is the math behind it? How do things dissolve? And then we'll get into different types of chemical reactions, including precipitation reactions, acid-base reactions, and what we call redox reactions. So some of this should be review from your first chemistry class. Some is going to be a little bit brand new. Math should also be a review with stoichiometry, but let's get started. First of all, from your notes packet, you should have gotten some definitions out of your textbook or other sources. If you were unsuccessful in that, then you probably want to pause the video and get these things written down. The first couple of things that I want to talk about is polar versus non-polar. This is a pretty important concept that we're going to come back to time and time again. But notice with this example up here, this is water. It is a polar molecule. So when we talk about uneven charge distribution, we're talking about this little positive here, that little negative there, there's a little positive there, how things are unevenly distributed. There's positives on one side, negatives on the other side. A non-polar molecule is going to have the charges evenly distributed. Hydration, solubility, solute, solvent, make sure that you're comfortable using all those terms. The next kind of chunk is talking about how do things behave when we dissolve something in water. So many times we can just describe acids and bases and salts and all kinds of compounds as being either a non-electrolyte, a weak electrolyte, or a strong electrolyte. And really all you're talking about is how well does something conduct electricity when it's dissolved in water. Keep in mind, everything we're going to be talking about in this unit, we're making an aqueous solution, so everything's going to be dissolved in water. So some things conduct electricity in water when it's dissolved, and other things do not. And then finally, acids and bases. So in other chapters, we will flush out many other definitions of what makes an acid and what makes a base. But for right now, we're going to stick to the Arrhenius definition that acids produce a hydrogen ion, bases produce a hydroxide ion. If it is a strong acid, think strong electrolyte, it completely ionizes, completely dissociates, splits up. It splits up into ions. Strong bases, again, also a strong electrolyte, will also completely ionize. It will also split up into its ions. If you don't remember, or how will you know whether something is a strong acid or a strong base, it's got to be on this list. So it's definitely worth pausing right now and kind of writing these things down in your notes. The ones that you really need to make sure, especially out of the strong acids, that you commit to memory right now are these three: hydrochloric acid, nitric acid, sulfuric acid. Very, very common strong acids that we're going to be using in a lot of different units. But basically, if it's not on this list, it's not a strong acid. Strong acids are strong electrolytes. Strong bases are strong electrolytes. Weak acids, weak bases, those are weak electrolytes. So it's a weak acid or a weak base if it's not on this list. And again, we'll talk more about that in other units, but right now you need to get to know those formulas and their properties as they pertain to solutions. So now let's talk about what happens when things are put into water. How exactly do things dissolve? So the mechanisms by which a solute and a solvent interact, it kind of depends on what you have. If it's an ionic compound, what I want you to notice is that you've got, here's little water molecules, and this is probably a crystal structure of sodium chloride. We've got positive, negative ions there. Notice how the water molecules are aligning themselves around the charges, and then what is happening to the overall crystal structure. So what's happening is you have the positive end of water attracted to the negative ion. So if this was sodium chloride, the positive end of water is attracted to the chlorine. The negative end of the water is attracted to the positive ion. So that would be the sodium. And ultimately, the crystal splits apart. We call this dissociation. A molecular, or also a polar substance, but it's found more as a molecule as opposed to an ionic compound. And again, in other chapters we'll further define that. But a polar substance that's not an ionic compound, but we also know it will dissolve in water, dissolves by a slightly different mechanism. The main idea here is that the molecule is not going to be pulled apart, but you will see, very similar to like with the ionic compounds, that the water attaches or surrounds itself or surrounds the molecule according to the charges, according to that positive and negative. So you can kind of see this is a molecule of ethanol. There's a little OH over here. The oxygen has a partially negative charge, hydrogen has a partially positive charge, and the water molecule is attracted to that particular part of the molecule. But it does not split apart in the way that an ionic compound would. And of course, a nonpolar substance will only dissolve in a nonpolar substance. If you remember from last year when we talked about how do you know something is going to dissolve, we used the phrase like dissolves like, meaning polar dissolves polar, nonpolar dissolves nonpolar. So at this level, you can't really get away with the phrase like dissolves like. It's just an easy way to sort of remember it. But polar can only dissolve in polar. Things can only dissolve in water if that molecule itself is also polar. If it's nonpolar, it will only dissolve in a nonpolar substance, which is the whole why oil and water do not mix. Okay. But we really won't be getting into the mechanism that much about how nonpolar substances dissolve. Okay, moving on to the idea of an electrolyte. What makes a strong, what is a weak, and what does this look like? The best way to sort of describe this is by watching this lovely video. How can you tell the difference between a weak and a strong electrolyte? So we will turn it over.
The term electrolyte is a term used when talking about solutions with water as the solvent. We'll demonstrate the property of being an electrolyte with an electrical conductivity tester like this. Pure water does not conduct electricity. I will put the electrodes of the apparatus into the beaker of water. There's no light coming from the light bulb. If I dissolve a material in this water and the light lights very brightly, the dissolved material is called a strong electrolyte. As an example, here is a small amount of table salt. I'm going to add just a little bit to the water and stir it up. As it dissolves, the ions of sodium and chlorine, which are charged particles, go into the water, which will now allow the solution to conduct electricity. So the ionic substance, table salt or sodium chloride, is a strong electrolyte. The term non-electrolyte refers to a substance which dissolves in water but does not allow electrical conductivity. Here is some sugar, which I will dissolve in the water. As the sugar dissolves, the light does not light up, so sugar is a non-electrolyte. Some acids and bases are also strong electrolytes. Here's an example of some hydrochloric acid. Only a little bit in the water, and about 10 drops will allow the light to light up very brightly. So the acid is also a strong electrolyte, therefore it's called a strong acid. Acetic acid, on the other hand, dissolves but allows very little electricity to go through the water. See how the light bulb gives off much less light with a lot more acid. Thus we call acetic acid a weak electrolyte, and it is a weak acid.
So there you go. We can classify substances as being either a strong electrolyte, a weak electrolyte, or a non-electrolyte, and use its property of conducting electricity to kind of tell us something a little bit about that particular substance. How much does it dissolve when you put it in water? And I like this picture because it also shows at the particle level what's happening. Here you see everything's completely dissociated, completely split apart. Here you have some things split apart and a few molecules together. In here you don't have any ions. It can't conduct electricity unless it's giving off some ions. So if you don't have those charges, it's not going to conduct electricity. And now it's math time. So let's talk about, once we dissolve something in water, how do we describe it? How do we calculate it? So there's a lot of different ways that we can describe concentration of solution, how much solute is in a given volume of solution. But in chemistry, the one that we predominantly use is molarity. Moles of solute per liters of solution. Different industries use other things, but the one that you really need to know for chemistry in particular is going to be molarity. There are some others that are mentioned in your book, but we'll address those as we get to them. So let's just do some sample problems. How do we calculate molarity? So for instance, we want to calculate the molarity of a solution by dissolving 1.56 grams of gaseous hydrochloric acid into 26.8 milliliters, and we want to know what that solution is about. So the first thing I need to do is convert my grams of HCl into moles, since molarity is moles of solute. In this case, my solute is the HCl. So I'm going to convert my grams into moles. And also molarity is in liters. I've been given milliliters. So I need to convert my liters, or I'm sorry, my milliliters into liters. 0.0268 liters. That's an L. Okay. And now I can go ahead and calculate molarity. Since molarity is moles per liter, I have now calculated moles. And I've calculated liters. So my molarity is going to be 1.59 moles per liter. Let's just do a quick sig fig check. 3 sig figs, 3 sig figs, 3 sig figs, and my unit is moles per liter. Here's another example. Typical blood serum is about 0.14 molar NaCl. What volume of blood contains 1 milligram of NaCl? So again, we're going to start with our solute, milligrams of NaCl. And I'm trying to figure out, so remember that molarity is moles per liter. I'm trying to get to volume this time, given molarity and given my mass. So 1 milligram of NaCl, first I'm going to convert that into grams. Yeah, milligrams, there we go. Okay. From here, I'm going to convert into moles, because molarity is moles per liter. How many moles of NaCl is that? Grams of NaCl. And now I'm going to use my molarity. So if I have 1 liter of the stuff, I know that its molarity is 0.14 moles. So the volume is going to be 1.2 times 10 to the negative 4th liters. So molarity is pretty useful. It's going to be a great conversion factor. In first year chemistry, you probably just learned how to calculate it straight out. But always keep in mind what its units are, moles per liter, because that's going to kind of be a means to an end for us. Alright, finally I want to wrap up this particular podcast with just how do we make a solution, because many times you guys are going to have to create your own solution, and what is the process that that's going to look like. So we have kind of 2 different examples here. One, you're going to be making a solution from a given solid, and one, you're going to be doing a dilution, say with a concentrated substance. So let's start over here. I need 500 milliliters of 0.1 barium nitrate, and you're going to be making it from a solid. So math is going to give you this piece. Okay, first we're going to need to do a little stoichiometry to figure out how many grams of the barium nitrate you're going to measure out. So I need 500 milliliters, and I know the molarity. So remember that molarity is moles per liter. So first I need to get that into liters. And if molarity is moles per liter, that means every 1 liter of barium nitrate has 0.1 moles in it. And now that I can figure out how many moles I have, I'm going to go ahead and convert that into grams. And that's going to give me 13.07 grams of barium nitrate. Okay. This is what we do all the time. Anytime we make solutions for our chemistry labs, that's the process that we go through. We got to figure out how many grams of solid we need to give the desired molarity. Now just a little bit of lab procedure. So this is called a volumetric flask. They're very, very precise up to that little line right there. So they're used only to make a particular volume. So the first thing you do is we're going to dump in our solid. We're going to add a little water just to dissolve it. Okay, so you can kind of see that we're putting in just enough water to dissolve. You get the solid to completely dissolve, and then you fill it up to the line. When it's filled up to the line, then you know you've got your 500 milliliters. You don't fill it up to the line right away because sometimes the substance will take in water to dissolve and sometimes it'll kind of give off water to dissolve. So your volume is going to fluctuate a little bit. So that's why this step of completely dissolving it first and then filling it up to the line is important. Okay, our second version, we're going to start with concentrated acid. Let's say, for instance, I need to make 250 milliliters of 3 molar HCl from a big bottle of concentrated acid. Concentrated hydrochloric acid is about 12 molar. So for this particular type of problem, I'm going to use a dilution equation. When you dilute something, the moles of your solute remains constant. All you're doing is adding water. So my moles of HCl is going to stay the same, but I'm going to be changing the volume, which is why this little version of the molarity equation works. Molarity 1 times volume 1 equals molarity 2 times volume 2. So now we're going to plug in our numbers. Molarity 1, well, that's my concentrated stuff. Volume 1, I need to know how much of my concentrated stuff I need to measure out. When I'm done, I need my solution to be 3 molar, and I need 250 milliliters of it. Okay, go ahead and solve for V1, and I will need 62.5 milliliters. So what I'm going to do is measure out 62.5 milliliters of the concentrated acid and then dilute it up to, in this case, 250 milliliters. Now if we're dealing with acid, the rule is AAA, always add acid to water. So in other words, you need to put in a little bit of water first. Then you're going to add acid. Then you're going to add your acid. Add, acid. Always add acid to water. Don't go the other direction. It gives off a whole lot of heat. Notice that we're filling it at about halfway, kind of completely dissolving it just like you did with the solid. Because again, sometimes the molecule will take in water or it'll give off water, so it gives you an accurate volume reading until you've kind of completely dissolved it. And then you bring it up to the line. And that's how you make a solution.